Okay, so Unit 2 is going to focus on Earth's atmosphere. Now, there's a lot to talk about with Earth's atmosphere, but mostly we're just going to focus on the way in which uh, the energy absorbed from the sun drives the various components of the atmosphere, producing weather and climate and ocean currents and things like that. But for today, we just want to focus on the structure of Earth's atmosphere because it's going to be important from an environmental standpoint. So, first of all, a lot of people seem to think that Earth's atmosphere is a lot thicker than it actually is. So a lot of people sort of envision that the Earth's atmosphere extends, a significant proportion of the Earth's diameter in space. When in fact, that's not true. The Earth's atmosphere is very, very, very thin. It's just this little tiny veneer. It's like the skin on an apple or something like that. It's so thin, and yet it's so precious because without it, we're exposed to the harsh energy that is being released by the sun, which we could never survive. Our DNA would just be torn apart if it wasn't for the protection that the atmosphere affords us. Now, it's held in place by gravity. So, an atom in the or a molecule in the atmosphere is pulled to the ground just like you are. However, they're also pushed upwards by collision with other air molecules, and so they form this layer. They're basically being pulled downwards and pushed upwards at the same time. They just float around in this little layer here, and this layer it's only like maybe like less than 500 kilometers thick. It's not much at all, uh, but it certainly is important. Now, if Earth had less gravity, like say the moon, then we may not be able to hold an atmosphere. So the moon, you see people on the moon from archival footage. You notice they're wearing these spacesuits, and that's because there's no atmosphere there. If there is, it's just super, super tenuous and thin. And the reason is that it doesn't have enough gravity to hold an atmosphere. Earth is much larger and has a greater pull, so it can hold that little veneer of air. But the moon doesn't have that much gravitational pull. So if a nitrogen or oxygen molecule happened to touch the surface of the moon, then what would happen is it'd be pulled downward by the gravity of the moon. That's true, but the atoms in the moon's surface are going to be wiggling, especially they're going to go quite violently because they're absorbing so much energy from the sun. And so if a molecule touches this vibrating lunar surface molecule, it gets thrown upwards at velocities that are so high that it basically leaves the moon and never comes back, kind of like a rocket being ejected from Earth. So we call this escape velocity. And so when molecules touch the surface of the moon, they achieve lunar escape velocity. They don't come back. So the moon doesn't have an atmosphere. On Earth, it has more gravity, so they might touch. First of all, the atmosphere keeps the planet from being that hot, the planet's surface. But even then, when they're pushed upwards, they're pulled back down by Earth's stronger gravity. So we get to have one. Lucky us. The composition of the atmosphere is something that I want you to know. At least not just here's what you need to know. Okay, ready? It's mostly N2, nitrogen, in the form of N2. And that is basically an inert gas that apart from nitrogen fixing bacteria, it just goes in and out of our lungs and doesn't do anything. About 20% of it is oxygen. That's the part that is so important for respiration. Carbon dioxide is a very tiny percent. Look at that. It's like less than, uh, 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 far less than 1%. Okay, so it's this tiny amount, like a 400th of a percent, basically. Uh, and then there's other components of it that you don't need to worry about. You just need to know that it's mostly nitrogen, it's about 20% oxygen, and that it's got these significant but still trace amounts of carbon dioxide, at least here at ground level. Now, atmospheric pressure is something we need to talk about here. So basically, pressure is caused by things being stacked up. So if I put your foot on the ground without a shoe on and I started stacking boxes on it, and the first box isn't so bad. The second box starts to hurt. About third, fourth, fifth, sixth, eventually I crush your foot. Why? Because you're feeling the weight of all the boxes stacked on top of you. That's exactly what happens with the atmosphere. Basically, here at sea level, you've got 500 kilometers of air molecules stacked on top of you, and they weigh something, right? They basically put pressure downwards on you, and it generates about 14.7 pounds of force per square inch. I'll just use that way of doing it. What we also call 1 kilopascal or 1.1 kilopascal, which is thousands of newtons per square meter. So this is just the consequence of all the air molecules stacked on top of you. Now, if you go up in the air, like here, you've got 14.7 psi. As you go up, there's less air stacked on top of you, so you only feel the air on top of you. So naturally, as you go upwards, the pressure becomes less. Here's a good graphic to show this. So here we're at 1,000 millibars. Okay, so 1,000 millibars is 1 bar, 1 barometric pressure at Earth's surface, and we see that as we go up, the pressure is going to go down. So before we even get to the top of Mount Everest, we've already gotten ourselves above 50% of the air molecules on the planet. And that's because the weight of them squeezes them in closer. So the first 5 or so kilometers of air has basically most of Earth's air. On Earth's surface, you can climb above half of Earth's air. That's why it's so difficult to breathe when you get to the top of these high mountains. If you go, maybe say 17 kilometers up, you're above 90% of the air molecules on Earth, and so on. So the less air there is above you, the less pressure is produced, and so we get this curve like this. And you can see by the time we get to, say 50 kilometers up, we're dealing with just trace amounts of pressure. It's still there, but it's just very, very, very weak. Now, as we observe Earth's atmosphere, and basically what happened was in the mid 20th century, early 20th century, people started putting balloons up that could go way, 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 way up in the atmosphere, and they carried sensors with them, and they collected data, and they found some interesting phenomena here. And basically, as a consequence of that and space exploration, we came to realize that the atmosphere is divided into layers. These layers, basically from the surface to the top, are the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. And each of them has unique qualities, and we're going to dig in on this a little bit here. Okay, let's start with the troposphere. You and I live in the troposphere. The troposphere is basically where most of Earth's air molecules are. 75% of them are here. It's where all of Earth's weather is, all the wind, almost all the water, all the clouds. Everything is contained within this troposphere, and this troposphere doesn't go up that high. We're talking it maybe goes up a little over 10 kilometers, and then all of a sudden you get to a place called the tropopause, where there's a change. Now, this change, the best way to delineate the boundaries between these layers of the atmosphere is by changes in temperature, it turns out. So for each of these layers, we have to discuss what the temperature behaviors are with altitude, what the trends are, and why. So with the troposphere, what happens is as you move upwards, what happens is as air moves upwards, the pressure goes down, so it pushes outwards. Well, if it pushes outwards, that takes some energy, and that energy has to leave the air molecule that's behind. And so since it did work, it has less energy inside it, and so it gets colder. So we find there's a very consistent rate of it getting colder, 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 colder. We call this adiabatic cooling. You don't need to know that, but we see that happening as we go up, and it gets quite cold. I mean, you might have noticed top mountains, it's always cold and snowy. It never thaws out. That's because of this cooling effect that happens in the troposphere. But that all stops once you get a little bit above 10 kilometers up. And then what happens is you keep going higher, but the temperature stays pretty much consistent, and all of a sudden it starts getting warmer. And that's because you've left the troposphere and you've entered the next layer up, which is called the stratosphere. Now, the stratosphere, strata just means layers. And so what they find is the stratosphere has a lot of sublayers that we're not going to worry about. But the main layers we have to worry about within it are known as the ozone layer. I'm sure you've heard of ozone layer. There's a lot of misunderstandings about ozone layer. So let's just try to set the record straight. Ozone, basically, we'll look at the next slide. How about that? But basically, this is the layer that contains a lot of ozone. And there's the various layers of it. And what happens is these ozone molecules have the ability to absorb ultraviolet light from the sun, high energy light from the sun. That would be harmful to us. It causes cancer. But what happens is it gets absorbed here. Well, remember, first law of thermodynamics, you can't destroy energy. So if I take incoming energy from the sun and I absorb it, it has to still be there. It takes the form of heat. So this layer gets very warm, and what we find is there's this general trend in warming. Now, this is not a temperature graph here. This is an ozone in parts per million graph with altitude. But let's just talk about a formation of ozone. So ozone is just oxygen. It's what's known as an allotrope of oxygen. So it's an O3 molecule. What you're breathing in right now is the O2 molecule. That's what's used for respiration. You would not want to breathe in just an O atom, because monatomic oxygen, it's got a pretty strong electronegativity. It would basically react with you and catch your lungs on fire. So that's not a good thing. But But what happens is ozone is formed in the stratosphere when the following things happen. So this is an O2 molecule, the stuff that you breathe in. Ultraviolet light from the sun hits it and breaks it into two O atoms. Really, maybe even an ion. It depends. All right. Now these ones here will end up reacting with other O2 molecules, and they'll form what's known as O3. And it's a fairly weak bond here between I think it's what's known as a coordinate covalent bond. Again, you don't need to know that, but this third oxygen that got attracted to this, it's on there, but it's not on there very tight. So we find that ozone is not a particularly durable molecule. But anyway, this is how it forms. Now, what's important is when it forms, this molecule here does not really block ultraviolet light. So ultraviolet light, when it hits this, it doesn't always cause it to break in half. Sometimes it does, but if it doesn't, it just kind of moves through. But when it does break it in half, it forms this ozone. Well, when ultraviolet light hits ozone, ozone then oscillates when it gets hit. So the energy of the incoming light causes it to wiggle, and that eventually gets turned into heat. So the important thing about the ozone layer is it's weird. It's formed by ultraviolet light, but then it blocks ultraviolet light. So ultraviolet light breaks O2 apart, forming O3, and then O3 absorbs ultraviolet light and prevents it from reaching the ground. So again, because this O3 molecule is absorbing high energy light from the sun, we can't destroy energy. It's got to go somewhere. It goes into heat. So what we find is after cooling on our way up, we hit the tropopause, and then what we find is we get those ozone layers, and it starts getting warmer and warmer and warmer. So through most of the stratosphere, there's this warming trend until we get to a height a little bit less than 50 kilometers up. And then we reach, just like we reached a tropopause, where the temperatures are paused at a certain, the change quit happening. The same thing happens here. It quits warming up, and we have this little zone where there's a boundary. And then we enter the next layer of the atmosphere. And the next layer of the atmosphere is known as the mesosphere, which just means the middle sphere. Now, the mesosphere is not particularly interesting, quite honestly. The main thing you got to know about it is that the temperature continues to drop, mostly because the air is highly rarefied. So 99.5% of all the air on our planet is found in the stratosphere and below. Above that, there's very, very, very little air, and so it's difficult for it to absorb energy. And so since it can't absorb energy, it just loses energy, loses energy, loses. In fact, at the top of the mesosphere, which is known as the mesopause, again, we have a temperature that pauses in its change here. This is the coldest part of Earth's atmosphere, and it's got a temperature down here around pretty close to negative 100 Celsius. But then after that, we enter the thermosphere. Now, the thermosphere, thermo meaning heat, why is that hot? If you look, it is the hottest layer on Earth. It's even hotter at the top than it is here on the ground. Why would that be? Well, for the same reason that the stratosphere is hot. It has to do with, it's got to get energy from somewhere. It's getting it from light from the sun. In this case, it's absorbing high energy ultraviolet light and X-rays. The ultraviolet light that was being absorbed here is of a slightly lower energy level. So we have ultraviolet light A and ultraviolet light B. And so this is the lower energy, and this is absorbing the higher energy. And so it gets hot when it absorbs that higher energy. So here's what happens in the thermosphere. In the thermosphere, I have an X-ray or a high energy UV ray interacts with oxygen or nitrogen, which makes up the bulk of the atmosphere from the ground to the outer space. Now, it comes in with enough energy that is what we call ionizing radiation. It takes this, I keep hearing a beep. It knocks electrons off of the oxygen molecule. And now what I have here is a positive O2 molecule. So what we find is there's a lot of ions up there. Now these ions, there's a few fairly interesting aspects of it. One is that you've probably heard of electromagnetic pulse. What they found is that if you detonate nuclear weapons up there, that it can cause a sudden movement of these ions, which makes a very large electromagnetic pulse, which can then fry out sensitive electronics. You're not going to have to know about that. I just thought I'd point that out because I think it's kind of cool. My Uncle Al, who just died recently at the age of 100, he discovered that by accident and had to be briefed by the get top secret briefing because he discovered this. But anyway, uh, the thermosphere is where we're ionizing particles of nitrogen and oxygen. So we make O2 and we also make NO because sometimes the nitrogen reacts with the oxygen. And so we're forming these ions and it generates quite a bit of heat. So the hottest part of the atmosphere is actually found here. So the thermosphere starts at the coldest part of the atmosphere, which is the top of the mesosphere, and it ends with the hottest part of the atmosphere, which is the boundary to the next and last layer, which is known as the exosphere. The exosphere is basically outer space, but what's kind of cool about it there is that the atoms are so far apart they just don't interact with each other. And if they're going to stay there, the only reason they can do that is they are in ballistic trajectory orbits, similar to a space shuttle. By the way, I should point out that the where the International Space Station orbits, it actually orbits in the mesosphere and the lower part of the thermosphere. So they're not really in outer space, but there's so little air there, it might as well be. Okay, so just to recap, so this is what a temperature profile of the atmosphere is going to look like, and it's very easy to see a delineation of the different layers. So here's the surface, we're in the troposphere. Temperature's cooled, so we get the tropopause. This is where all the wind and weather is going to occur. Now what happens is I enter the stratosphere. It begins to warm up as I go up through the stratosphere. Why? Well, because we have ozone layers here that are capturing lower energy UV light and turning into ozone, and that produces quite a bit of heat. Then we get to the stratopause, and above that, the temperatures start to drop. We're in the mesosphere here, and it's just very rarefied air, very air molecules far apart. They're not able to absorb much in the way of energy, so they just cool down, cool down. We get to our lowest temperature here at the mesopause. Then we get into the thermosphere. In the thermosphere, we're absorbing X-rays, and we're absorbing high energy UV light, and we're using it to ionize oxygen and nitrogen, and the temperatures get quite high. They can get significantly higher than they are here on Earth. And then beyond this, we have the exosphere. We just have uh, molecules that are orbiting the Earth like satellites. So that's it. Please be ready to answer some questions about this when you come to class, and I'm going to assign you a lab that involves your ability to interpret data about this.